going to review a lot of the concepts from throughout this year. It's also going to kind of bring it all together. So, talking about linear regression, when we feel after looking at the form, because we have to plot it to see the form, looking at the direction and the strength, we think there may be a linear relationship between two quantitative variables. Okay, then if we want to answer the questions, is this linear relationship, is it really just happening by chance, or is the slope in fact equal to some value? Is the slope really just nothing? That would be looking at this from the perspective of a test. Now, if we are wondering about this slope and thinking about this change in y for every increase of x units, and we're wondering about this margin of error for this estimate of a slope, so we have a slope and we want a window of estimates, then we're looking at this from the perspective of a confidence interval. And so we're going to do both of those things for the slope. And so that's looking at inference on the linear regression line, deciding if that slope is the result of chance variation or is that slope the result of something else. So here is this example from chapter 3. It's relating the eruptions for 222 recorded eruptions in a single month. So it actually is the population for that month. So in fact, linear regression would not be, inference would not be appropriate for this because we actually do know the population. But we can still do linear regression because we can look at the form, and when we look at the graph, so you must graph to do this, this shows a roughly linear form, so that means it would be appropriate for linear regression. Then when we, so that's the form, then we look at the direction, and in this situation it seems to be positive. And when we run our, could have been negative, but this one's positive. And then we also look at the strength, and to do that, we would calculate the R value, the correlation coefficient, and those values are going to vary between -1 and 1. Remember, there are no units on R because it is based on z-scores, which don't have any units. And if you have a -1, that's a perfect negative relationship. A +1 is a perfect positive relationship. And if you have, the closer you are to R equals 0, that would be no relationship. Slide this up. Okay, so if we take a simple random sample of 20 eruptions, now inference would be appropriate because this is based on a sample, and we could find a linear regression line just based on the sample data, and we can compare that to what we really know is the true population line. So just to show how this process works. So if we think about our sample equation was y equals a plus bx, with a being the y-intercept and b being the slope, we can actually write this as a population symbols. And I know this is going to be a little annoying that we're using alpha and we're using beta, but they like to use Greek letters for the population values. And I know that we use alpha for type 1 error, and also we use alpha for what we're checking when we're comparing our values to that 0.05. And I know we use beta for the probability of type 2 error, but don't confuse these population symbols with those errors. So they just are repeating those symbols, but what can we do? We're just not all that creative. So these were sample symbols, and these are population symbols, which will be important because if we're writing our null hypothesis, we need to use population symbols. And basically, in this situation, those sample values, we hope, are unbiased estimators, and they actually are, of the population values. See that on the next page. Okay, so to the next page where we've done more than one sample of 20 eruptions. Okay, so the first sample of 20 eruptions resulted in this sample equation. The second sample of 20 eruptions, which may or may not have included some repeats, it resulted in this. And the third one resulted in this. And if you were trying to do all the combinations for a sampling distribution, that would have been 222, choose 20. This is definitely going to have an overflow in your calculator, but we have just done 3. Okay, simple random samples of n equal 20. So if you look at the slopes of these regression lines, we got well, that's a little confusing, that little line there, but we've got 10.2, we got 7.7, and we got 9.5. These vary a bit from that population regression line of 10.36, which we know is the real value for those the population of 22 eruptions in that 1 month. But this pattern of variation can be described by this approximate sampling distribution that we're getting for the slope. And so if we did many, many tests of trials of size of n equal 20, and we did many, 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 many trials, you can see from this Fathom software, this is 1,000 trials actually, you can see that this does become an approximate sampling distribution, and it does have the situation where it's starting to look like it's trying to be nearly normal. It's definitely bell-shaped, but with n equal to 20, it does not meet CLT. However, what kind of test statistic will we probably be using in this situation? It not being a proportion, it being a means. This is a t distribution. And remember, at levels of 20, it's very robust at n equal 20. Between 15 and 30, it's very robust. Make sure you don't have any outliers. That would be something that would be a problem. So we are going to be able to do t intervals, and we're going to be able to do t tests for the slope. Okay, and we're going to do that in the next video. I'll do that. This video is just kind of introducing everything. Okay, so shape, outlier, center, and spread for these this distribution of these slope values. It's roughly symmetric, it's unimodal. The normal probability of these values is showing that it's approximately straight. So that is giving us a good indication that this is, nearly normal. And as you can see, the center of our sampling distribution is really looking like it's close to that true population value of 10.32. Okay. And then if we look at the standard deviation of these 1,000 values, which we're going to look at later, we'll see that the standard deviation of this sampling distribution is 1.30, even though, like, when you do the standard deviation of these values, you get 1.31. We actually, because slope involves both x and y is involved in slope, because it's change in y over change in x, we actually need to use n minus 2 when finding standard deviation of slope. Okay, because this one here was using n minus 1 to find standard deviation, but I don't know if you remember way back in chapter 7 looking at unbiased versus biased estimators. And in this, that would be if in repeated sampling, are we going to get close to the true value? And in this case, using n minus 1, it's a biased estimator, meaning that it's going to either overpredict or underpredict. That's what biased estimators do. But if we use the n minus 2, we get something, an unbiased estimator, meaning that in repeated sampling, it's going to be centered around the true standard deviation of the slope. So that's why we use that, and it will see that it's on the formula sheet. And in about 3 pages, we'll look at those formulas. But before we do that, what are our conditions for regression inference? So just like before, where we're looking at the residuals and we're trying to make sure that there is evidence of a linear relationship, we have this mnemonic device liner, and that's going to help us remember the things that we need to check when we are looking to see if we're going to be able to do regression inference for the slope, for the true slope of the line, to see if that slope is that slope great? Is it a positive slope? Is it a negative slope? Or is it just any kind of slope at all? Okay, so first of all, we have to graph the data and look and see if the form, direction, strength, that's looking at does it look reasonable that's linear? We are going to be wondering if things are independent, because that's the condition for our inference. We're going to be wondering about it being normal, and specifically we're going to be looking at the residuals. Are they looking like we have something nearly normal in a histogram? Okay, we're going to be looking for equivariance. So when we do a scatter plot of the residuals, does it look like we have random scatter of these residuals, not really over predicting or under predicting scatter plot of residuals? And then is the data random? Because of course, if we don't have data that's random, then it's probably got some kind of bias built into it, or it might even just be worthless. So looking for a simple random sample would be a good idea in that situation. Okay, so we're going to check our conditions before we do anything. And so here's basically summarizing your steps. You can read through that. On the next page, we're going to see if you can identify what we're looking at. What are we looking at? L, I, N, E, or R? Let's look. Okay, so we've got this helicopter experiment from page 738 in your textbook. They have 14 helicopters. They're going to be dropped from 5 drop heights. And the team of students are going to release 70 helicopters at these predetermined order, but it was done randomly. And they're going to measure the flight time in seconds. So you can see, like, for example, at this drop height, there were all the results of what that helicopter was dropped at. So the first thing is, when you look at this first graph, what kind of graph is this? This is a scatter plot of the data. And so what are they trying to determine here? This is flight time in seconds versus drop height in centimeters. Okay, so what is this trying to decide? They are trying to decide, does the form look linear? And so let's look at that. If I make a rectangle around this, it does seem to have a linear form. Also, you want to be looking at the direction from this graph, and I would say it is positive. And then if you look at the strength, and it's also helpful to know what the actual R is, because that would give you a really good idea. So if I knew what R was, that would help. But just from a rough glance at it, I'm going to call it moderately strong. Okay, so that's satisfying the L of liner. Okay, so what's this next graph of? So this right here says residual. So this is the scatter plot of residual. The residual would have the same units as y, because residual is how far off your predicted your observed y is from your predicted y is from your observed value, because you remember you would go y observed minus y predicted, okay, to get the residual. So that's going to have, the residual is going to be in seconds versus drop height, and that was in centimeters. And on this one, we're looking for it to look like random scatter or equal scatter. Equal probably shouldn't have used the word random there. Really, it's like equivariance scatter. So chance scatter, not looking like there's any kind of pattern forms, no pattern evident. And that is checking the E. So it's also confirming, when we see this equivariance, that confirms the L as well. So it's satisfying the E in liner, but it's also helping to confirm that L. Okay, what's this graph? This is a histogram of the residuals. So it's just the residuals down here, their units being centimeters. And it's a count of how many residuals were in these intervals, these bins. And so I probably have my residuals in L4 of my calculator, and so I'm doing a histogram of just L4. And in this, I'm looking for it to be symmetrical. I'm looking for it to be bell-shaped, unimodal, and that is looking at our shape, outliers, center, spread. I don't want any outliers, and that is going to satisfy the normalcy condition, so that is satisfying our n. In order to make sure that there are no outliers, I would run a quick box plot, and that would confirm no outliers. All right, and then this last kind of graph here, which is option 6 on your calculator, and this is of the residuals again, and this is a normal probability plot. Of the residuals. Remember, that's option 6 on your graphs. So again, with the L4 list. And this is going to confirm, again, the n, that we really have something that it's not just looking like it's nearly normal. This being straight is evidence that it's really nearly normal. So that would be that we have checked we have now checked the L, we have checked the N, we have checked the E, but that means we still have 2 other things to check, I and R, but we're used to checking those as our conditions. And so make sure you run through those conditions to get that independence and randomness, which by now I think that's probably second nature. So when you are looking at this and you see a problem and it uses alpha and beta, make sure you don't confuse them with the type 1 and type 2 error. We just couldn't think of different letters, I guess. I don't know, but like they maybe 2 different clubs were thinking of the letters. But here's our population symbols. So that would be parameters. But if we're going to go through and we're going to do the least squared regression line, we're going to need to know the standard deviation for the slope, because if we're going to find a test statistic or we're going to do a confidence interval, we're going to need to know that standard error of the statistic, that's standard error of the slope. And in order to find this, we can look on our formula sheet. This is the standard deviation of the residuals, and there's that n minus 2 making this unbiased. I'm going to switch to the formula sheet where you'll also see this. And so we have to realize that the standard error of the residuals comes into there. And we'll see the standard deviation of x. This is just the x list. And then right down here, we see this n minus 1, which is helping us make this thing an unbiased estimator sheet. On the second page, you can see at the bottom of the page, sampling distributions for simple linear regression. So if we're trying to look at the slope, our best estimate of the population value will be the population value. Make sense? Right here, just like when we were looking at for means, okay, It is very rare that you would actually have the standard deviation of the population. If you did, you probably really know everything about that sample or about that population. So realistically, that's probably not going to happen that you have the population value for slope, that you're going to be able to put that in there. More realistically, you're going to be using the standard error of the sample statistic. And if you were doing a confidence interval, you absolutely would need to use the standard error. But more realistically, we're going to be doing t-tests on the slope and t-intervals on the slope. And so we'll be using these values over here, where the standard error for the slope is, there's the formula, and this is the standard error for the residuals, and this is the standard deviation for the sample slope, which this same formula, if you look back to over here on the first page, there's that same standard deviation for the sample for the x values. So that one can be gotten right out of the calculator when you do, one var stats on a list. That's the sample value.